In this article, I will briefly explain how the gamma value is solved when you are fitting a dataset to a 3-parameter weibull, so that you have enough knowledge to decide whether you should avoid this analysis. I will also provide an example that demonstrates an appropriate use case of the 3-parameter weibull distribution. The parameters of a 3p weibull PDF function are beta, eta, and gamma. Beta, also known as shape parameter, is a positive value that governs the rate at which the failure rate changes over time. If beta is less than 1, the failure rate decreases over time, indicating the population is getting more stable, in terms of failure, as it ages. If beta is equal to 1, the failure rate is constant. If beta is greater than 1, the failure rate increases over time. Eta, also known as characteristic life, represents the time at which 63.2% of the population fails. Gamma is a time shift term used to modify the original 2-parameter weibull distribution. If gamma equal to 0, the 3-parameter weibull reduces to a 2-parameter weibull distribution. A positive gamma means that item in the population will not fail before time t equal gamma. From reliability perspective, this is a desirable attribute. What if the gamma is negative? Does it mean that the items from this population can start to fail from a negative time? Note that in reliability engineering, we are only interested in the positive time domain. As a reliability engineer, the main reason to use 3p weibull for your dataset is that you believe that a no-failure time, or a positive gamma, exists in your population, and you hope that the analysis can tell you this value. Consider the following 2 time-to-failure datasets, Dataset 1 and Dataset 2, which are generated using Monte Carlo simulation from 2-parameter weibull with the parameter beta and eta equal to 9 and 3600, respectively. Both the datasets are fitted with 2-parameter weibull using rank regression on X, and the results are shown here. From the contour plots, there is a significant overlap between the 2 contours. That is, that there is no statistical evidence that the 2 sets are different. You want to know if gamma exists, and so, you proceed with the 3p weibull analysis. Perhaps you are convinced that it is not possible to fail within the first 1000 hours. Note that you are expecting a positive gamma. Now, let me explain how gamma is calculated using Dataset 1. First, the points are plotted on the probability weibull graph. A 2p weibull line regresses along these points. Notice that the points form a curvature facing downward as shown here. By reducing the times to failure values in the dataset by an appropriate constant, that is, gamma, we can remove the curvature. Let's subtract 2965 from all values in Dataset 1. Now we plot these adjusted points on the probability weibull graph. The curvature is not visible anymore. The gamma value is 2965 hours. The software search for a gamma value such that the adjusted dataset does not form a curvature. Based on the new straight line, the beta and eta are now 0.7611 and 485.8 hours respectively. Now we can plot the 3-parameter weibull curve by adding gamma value to the straight line as shown. We have just fitted the original dataset with a 3-parameter weibull. Let's proceed to analyze Dataset 2. The expected gamma value is close to 2965. Since smallest failure point for Dataset 2 is 2850, it should be somewhere below 2850. Notice that the data points form a curvature facing upwards. To form the best possible straight line, the gamma value is about minus 5.9 million hours. We have a negative gamma. The corresponding beta and eta are around 1,400 and 59,000 respectively. And we have a beta value that is way beyond 50. As a side note, a large beta means that the failure rate increases very sharply when the age is approaching eta value. Personally, I would switch to other distribution, like normal or log normal if the beta is greater than 20. These two datasets were generated using Monte Carlo simulation with two-parameter weibull. There was no gamma value, but we can always come up with a gamma by fitting a three-parameter weibull. When you obtain data from your lab test, or collecting data from the field, or generate random data through simulation, there is a 50% chance that your dataset forms a downwards curvature. In that case, you get some positive gamma. Otherwise, you get an absurd negative gamma. Given that you know the math behind this analysis, would you still trust the gamma value even if the result looks reasonable? What if we use MLE solution instead of regression method? Well, I will not go into details about applying MLE for 3P weibull, but I will just state that MLE provides equally absurd results most of the time. Let me end my commentary with an example of an appropriate use case of three-parameter weibull. The following dataset contains arrival time of a spare part from a manufacturer. You need a distribution to describe the lead time for simulation purpose. As shown here is the historical lead time dataset. You are aware that the admin plus shipment time is 27 days, that is, lead time cannot be short than 27 days. You can set the gamma equal to 27 days, and here is the adjusted dataset. Fitting it to two-parameter weibull, we get beta equal to 1.64 and eta equal to 6.5 days. So, the distribution can be described using a 3P weibull with beta equal to 1.64, eta equal to 6.5 days and gamma equal to 27 days. This example illustrates the case where gamma is a value you need to provide, and then transform the data for fitting a two-parameter weibull. It is very unlikely to determine via statistical analysis that the admin plus shipment time is 27 days. The analyst knows this because they understand the situation in which the data is collected. In conclusion, we cannot expect that one could extract a gamma value through fitting the data to a three-parameter weibull. Gamma should be a quantity that is known to the analyst. If you have no knowledge of the gamma value, stick to the two-parameter weibull. Thank you for viewing this video.